All right, so welcome to the AI course. From today we are going to talk about the technical aspects of AI. And before I start, I want to mention that while I am going to be presenting the course, I am really standing on the shoulders of giants. In other words, there are a lot of people who have taught AI really well, taught AI probably much better than me, taught AI, I have learned AI from them and so on and so forth. And I have learned from many such people, and the slides that I will be using will be stolen from different places, of course, with some permission, I would say. And so because of that, we will be sort of taking interesting bits from wherever I found and combining them in the course. I should also point out that I am going to credit all the people I have taken slides from in the first slide, not on individual slides, but I really thank them for developing this course for me and for themselves and for the field further. Okay. Now, AI course is being taught in pretty much every department, right, in the world, every top department in the world at least. And if you look at the AI courses in different institutions, you may find sometimes the overlap between topics is limited. There are many ways to look at a broad field like AI. I remember that when I would go to AAA conferences as a student, there will be 8 or 9 parallel tracks running, and sometimes as a young student, even though I was a researcher in AI, I may only understand things about one track and not understand anything about the other 7 tracks. It's a really broad field. And the reason it's a broad field is that AI is not just a technical subject, and we will understand it more and more over time, but it comes from a philosophy. AI is not a problem which has one solution or 2 solutions. AI is a general problem, a philosophical problem, which has many manifestations into concrete problems, which have many different solutions. So, a AAA conference or an AI conference often thinks of itself as an umbrella conference, which brings all these people together. Because AI has so many diverse subfields, any course cannot do justice to all of them, any limited time course. And therefore, if you look at the book, which is the Russell and Norbeck book, by the way, how many of you now have access to the book? Very good, very good. I am very happy to see that at least 20% of you have access to the book. This is only the second class. So, by next week, I hope all of you will have a copy of the book with you. As you must have seen, for the people who have looked at the book, it's a big fat book. And there is no way we are going to cover the big fat book in the class, right. So, any instructor has to make some calls on what it is that they want to cover in the course. Now, I think of it as a breadth course, right. A breadth course therefore may not be deep, right. So, usually the trade off is between broad and shallow versus deep and narrow, right. If you are one person who is broad and deep, all the power to you. I mean, I respect you, but most people are not such people. Most people are either on this side of the coin or that side of the coin. And in fact, you are undergrad students, so it is your time to learn something about everything, right. It is your time to be broad. Once you start doing a research project, once you go deeper into a particular assignment, once you go into a specific course project or whatnot, that would be the time for you to go deeper into something, and we can only go deeper into a few things, not too many, right. So, I am taking a view that this would be an introduction to the breadth of ideas in AI. So, I am going to introduce an idea, and that idea, if you are able to capture it, the core of it, and have it with you, it is going to help you in wide variety of settings, not just in the specific topic in which we learned that particular idea. So, if you are a general computer scientist, not interested in AI in the long run, you will still get a point of view and a set of general tools that will help you in attacking a new problem. And I am assuming that almost all of you will go into the industry or somewhere where you will be solving problems. I am not saying that you will be solving computer science problems also. You will be solving problems, technical problems at some level, right. And this AI way of thinking is going to help you, and that particular way of thinking we will introduce in the next week. For now, we are just motivating them and talking about what is AI, right, and the history of AI. And if you are a serious AI enthusiast, if you want to make AI your career, either in research or in further study and a job and so on and so forth, This would give you an introduction to a lot of topics. This will teach you about search, then you can go and take a heuristic search course. This will teach you about some Bayesian networks, probabilistic graphical models, then you can take Parag Singhala's course in probabilistic graphical models or Daphne Koller's course. You know about Daphne Koller? Daphne Koller was one of the founders of Coursera. She was a professor at Stanford. Her probabilistic graphical models book and her course is sort of the most famous course in this particular area. You will learn a little bit about planning and decision making. From there you can take a full blown course on reinforcement learning. For example, Parag Singhala is teaching a reinforcement learning 800 level course in our department this semester. Now you are not ready to take that course without doing the AI course which gives you the introduction. I mean, you can always pick it up, but eventually this course prepares you to take that advanced course if you are interested in, and so on and so forth, right. So there are many subtopics of AI, and this particular course is going to introduce all of or many of them to you. Okay. The other decision as an instructor we have to make is what do we focus on even within the topics that we are going to explain, right. And here you all know about theory and practice, theory and applications. Those are the two extremes of any scenario, right. But there are two more steps in the middle the way I think about it. There is the theory, there is the modeling, there is the algorithm, and then there is the application, in my view. Okay. And let us think about this from an example, and this is very important. This broad understanding of any problem is very important. So let's say I am in 2004 or 2003 and I am trying to create a MapQuest or a Google Maps. And there I need to decide that I have the whole map of the world. I need to figure out that I want to go from location A to location B. What is the best way to reach location B from location A? Okay. Now, this is a real problem. This is a real application, right. Now, the first thing you will have to do is to make it into a computational problem. You are not going to talk about which car am I driving, you are not going to talk about whether there is a gas station on this particular road or not. For now, I am going to abstract out all this information. I am not going to talk about whether there is a pothole in the road. I have to abstract out all that information into a simplified, approximated computational problem. And what will be such a computational modeling? Can you think about it? It's very easy, you have done this. Graphs. You will take the model, the computational model of a graph. Now, a graph has node and edges. So, you will say, for my problem, what is the node? So, you could say that any intersection is the node. See, we are talking about roads and locations. We are not modeling every coordinate in the location. We are abstracting it out. If we start modeling every coordinate, then it will be impossible, right. Every little point, we can't model that. We have to abstract it out. So, in our model, we will have graphs. A node will be an intersection. The edge will be a road segment that connects two intersections. Then we can additionally have a weight on the edge, and the weight could be, in this case, length. Length is one possibility. Some people will say time. Now, you have to say, oh, in the morning the time is different, in the evening the time is different, in the daytime the time is different, if there is an accident the time is different, if it is raining the time is different. Which time? It is an abstraction. So, initially we will say, I do not want to worry about morning, evening, raining, I will just take some average time. So, I will keep my Google cars going all around the city at different points in time, and at each road, however time it takes, I am going to just average it out, or take the if not average, one deviation or whatever, right. Then now I have converted into a graph. Now, notice this is called, can you guess? Modeling. This is modeling. Okay. Taking a problem and converting it into a computational problem, this is modeling. This you have to do in everything in the world if you are a computer scientist. You will never get a computational problem, almost never, unless you are a theoretical researcher, which will start from some model. You will always, in the world, you will get some real problem, you do not even know how to start modeling it into a computational problem. Often you would see that for a real application, a lot of the magic is in modeling. Because once you model, Somebody sometime has already solved that problem. Once you model this as a graph and model on the graph as a shortest path problem, now all the literature on shortest path problems becomes applicable here. You don't have to really be creative in solving this specific problem, you just now have to read up and check what are the various shortest path algorithms. You know, there is a Bellman-Ford algorithm, there is a Dijkstra's algorithm, there may be 20 others. You just quickly go look at which one is the right one for this fit. Bellman-Ford is much better if you have negative edges. We don't have negative edges, nobody is going to gain time. You are not time traveling here, right? So you don't need Bellman-Ford. Let's do something simpler, and so on, right? I am not getting into the specifics of how Google and Microsoft made their map engines. That is called the algorithm, right? We modeled it as a problem, then we chose an algorithm for it. We may have to innovate there, but that's the algorithm. Then we implement the algorithm. And when we implement the algorithm, we have to decide on, you know, what is the full graph. Now, when I am going from IIT Delhi to Ames or Horse Khas metro station, do I need to have in my graph the edge from, you know, the highway edge from Seattle to Portland? I don't. The whole graph of the world is huge. We don't need the whole graph for every problem. So how do we cut it, slices, dices, where does the map get stored, which part of the map do we put in the memory, etc., etc. All of these parts would be parts of the application solution. They also always interact with the algorithm, obviously, right? And last but not the least, what can I prove about them? Can I prove that I will always get the shortest path? Under what conditions will I always get the shortest path, etc., etc.? That will be called the theory. So now do you understand with an example? This is called, you know, explanation by example. Application, modeling, algorithm, theory. You can I guess I don't know what will be the right order. The order is because you can prove theorems about the problem, what is the complexity class of the problem. You can prove theorems about the algorithm. So therefore theory interacts with both the modeling as well as the algorithm itself. The algorithm is implemented in the actual application. Now, in this course, we will tilt towards modeling and algorithms. In your assignments, you would do application, and we will not very much bother about theory. And again, this is a choice. Once in a while, I will introduce some theorems. Maybe I may prove one, but mostly the book has theorems and proofs. We will talk about the theorem, but not talk about proofs more often than not. We will mostly focus on how it gets applied, how a new problem can get modeled, how a model may have solutions, what are the properties of each solution, and so on and so forth. This is part that we are going to focus on in this particular course. And of course, you can have an AI course where you go deep into the math and the theorems and the theory, and that is not what we are going to do. Okay? Any questions on this? All right.